All right, so we continue with the operational amplifier. So just to recall, let us have the equivalent circuit of a ideal operational amplifier. So we know that it has a inverting and non-inverting input terminals. They can be represented like this. And to these two terminals, we have the input voltage sources connected, called as V1 and V2. So that's your inverting input. That's your non-inverting input. And the currents that are generated because of the applied inputs, let's say I1, and this is I2. And we know that no current, ideally no current can enter inside the operational amplifier. Therefore, these two currents are zero. And then inside the operational amplifier, what we can model is this dependent voltage source is connected to the power supply, which is common ground here. This is common ground. And this is an output supply or output voltage. Right over here. So this is an output terminal. And the value of this dependent voltage source is A times V2 minus V1. All right. So that's the difference between the two inputs. So we know that this differential, it amplifies the differential signal. So we can say that this is V2 minus V1 or A times VID. And VID is the difference between the two input terminals. So right over here, we'll say that the VID, that's the difference between the two input terminals. And I1 and I2 are zero because of the infinite input resistance across these two terminals of the operational amplifier. So let us understand a new application. We try to study a new application with this. So we've seen the inverting amplifier, and now we have the same inverting amplifier where we have these two terminals. And to the inverting terminal, instead of one input, we have several input. Let's say we have register R1, R2, and this is up to Rn. And the input signals are V1, V2, up to Vn. The currents that are created are I1, I2, up to In, and that's the total current, which is a summation of I1, I2 up to In, right here. And then we have this feedback configuration where fraction of the output voltage VO is fed back to the inverting terminal at this node through this resistor. Let's say we have RF. Okay, and apparently the positive input terminal is connected to the ground, and this amplifier has infinite gain ideally. So what we see here is that the current that tries to enter the terminal tries to enter the operational amplifier through this negative input terminal or through this positive input terminal, they are all both zero. So let's say IN is zero and IP is also zero, where the positive P indicates positive and indicates negative. These are the terminals. So these two nodes are, let's say this is our node V2, this is node V1, okay? And we know that we can first write the expression for the total current that is coming right over here, I, which is the summation of I1, I2 plus up to IN. All right, and this is by Ohm's law, they are V1 over R1, V2 over R2 plus up to Vn times over Rn. So that's your input current. Similarly, so as we know that this current comes over here, and since no current can go inside the operational terminal, inside the op-amp, so this current tries to enter this current. So this current through these feedback resistor called as IF is nothing but this current I. Okay, so expression for these two currents, we can always write IF would be the voltage drop across this resistor, which is V1 minus VO. That is the voltage at these two nodes divided by the value of RF. Okay, so what we see here, V1 is 0 minus VO over RF. Why V1 is 0? Because we know that this V2, because the gain is infinite, right over here, the difference is different between these two, that is VID, these two terminals. VID is the difference between the two terminals is 0. Okay, so we know that VO over A is V2 minus V1, or VO over A is VID. So when gain tries to approach infinity, the VID, which is the difference between the two terminals, tries to approach 0. So since V2 is connected to 0, the V1 is the voltage at this node V1 is forced to be 0 ideally. Okay, and that this assumption helps us to simplify this analysis. Therefore, V1 is equal to 0 here. So we know that once that is by the Kirchhoff current law at this node, we can equate the two current. I is IF. So we write the values of these two current plus Vn Rn, that equals to minus VO over RF. And we can get the value of VO to be minus RF. In bracket, we'll write this expression. So as we can see that the output voltage basically, okay. So if we say that V1 equals to V2 equals to Vn, and that equals to V, so we can write this expression as minus RF V by R1 plus V by R2 plus V by Rf, and that simplifies as minus Rf more R1 okay, that is the V O over V right here. Just to correct this one, we have this expression V over Rf. Here we have Rn actually. Right, so Rn. Okay, so we see from this expression, this output expression, we simply can choose the different values of R1, R2, and therefore we are able to tune the, to modulate the output voltage, right, for a given value of Rf and for the voltages applied. So this kind of circuit is called as summing amplifier, or operational adder circuit, all right, or weighted amplifier, weighted summer. So this is all summer. So using the operational amplifier, we can create these applications, and we can see that the weight can be tuned, weight can be assigned by choosing the values of these resistors, and based on that we can have the expression for this. And of course since it has a negative sign right over here, so this is the inverting summing amplifier. So what we see here is that operational amplifier can be configured as an adder, where each input applied can be added right here. These are the inputs with different, and R1 and R2 are the values of these registers that can be used to tune this, design this circuit. Okay. Let us take an example of another circuitry right here. So this, instead of applying input to the negative terminal of this operational amplifier, what we do here, we apply the input signal to the positive input terminal. Let us call it as input signal Vi. And the negative terminal is as usual connected through the resistor, and it is other end of the resistor is connected to the ground, and fraction of the output voltage is fed back to the input. Since this is a feedback, we call the resistor to be feedback RF, feedback resistor, and at this node. So this node is your V1, this node is V2. All right. So how to analyze this circuit? Again, we can come back to the analysis. Now this V2, we can have this expression VO over A, which is V2 minus V1, or VO over A is VID. So when gain tries to approach infinity, when the gain is infinity, VID tends to 0. Okay, so it means VID, which is V1, V2 minus V1, that tends to 0. So V2 has to be equal to V1. Okay, with VID 0. So V2 is at the voltage at V2 at this node is nothing but what we apply is the input signal source Vi. So V1 is nothing but V2, and the voltage at this is also Vi. Okay, and because of this voltage comes over here and the other end of the resistor is grounded, the current that flows through this resistor is indicated by I1. Okay, and similarly we have this current. These two currents are the current through R1 and RF is same, because we know that the current that tries to enter the operational amplifier, let's say IN, is 0. Okay, similarly current that tries to enter the positive terminal of the op-amp is 0. Why? Because ideally the operational amplifier has an infinite input resistance, so no current can enter inside these two terminals. So these two currents, IF is nothing but equal to I1. Okay, so that's how we can get the expression for this one. So how to simplify? We simply write I1 is nothing but V1 by R1, and V1 is nothing but Vi by R1. Okay, due to the virtual ground concept. So the difference between the two, terminal, that is positive and negative, is VID. Okay, so that's our equation, and similarly I1 is equal to IF. We can write the expression for the IF will be VO minus VI. This is because this is the voltage drop across resistor divided by the resistor value RF. Okay, so we simplify these two currents. Value of I1 is VI R1, that is VO minus VI by RF. We try to simplify this. So final expression VO over VI can be written as the ratio of these two resistors. And that can further be simplified as +1. Okay, so we see here this is the gain of the amplifier, and since it has a positive value, so this configuration is called as non-inverting case of the amplifier. So we've again seen that how the virtual ground concept and the theory helped us to simplify these analyses and to obtain the expression of this one. Another point that can be noted over here, we see that if we take a look at this, we have this output terminal right here, and voltage at this node is the input signal source that we have, and we can get the expression for the voltage at the node V1. So voltage at the node V1 can be seen here. We see that this is nothing but forming a voltage divider right till here. Okay, so we see that the node voltage at V1 can be written as, this is your output voltage, and then we have this resistor RF, and then we have resistor R1, here at node V1, we are interested to obtain the voltage. So V1 would be VO times RF divided by RF plus R1. Not really. We made a mistake here. So it would be R1 divided by R1 plus RF. So that's the fraction of the output voltage that we'll have across the R1 right away here. So this is again happening because of the infinite gain and the virtual ground concept. So what we can write here, we have the expression Vi because we know that V1 is nothing but Vi. So Vi would be Vo times R1. This is V1, okay, that equals to Vi. Let's write it proper. V1, and this is nothing but Vi, and that is the expression right here. Okay, because of we know that V1 equals to V2. This So from this, can we get the expression of VO over VI magnitude? Yes. So we see here that is R1 plus RF divided by R1. So this is again 1 plus RF over R1. So that's the closed loop gain. This is the closed loop gain of non-inverting amplifier. Okay, so let's say let's understand what is the use of feedback and how feedback helps us to maintain the properties of the operational amplifier. So we have this amplifier. Let us take the case of inverting case, non-inverting case actually. So we have this configuration. And to these positive terminal, we have the signal source applied and voltage at node. This node is V2, voltage at this node is V1. Okay, and other configuration, we know that no current can enter inside the operational amplifier. So IP is 0, IN is 0, and this potential between these two terminals, that is VID, is the differential voltage across these two terminals. All right, so this because of the virtual ground concept, the V2 is equal to V1 is equal to V2, okay, which is VI. VI. And since the VI comes over here, the current that will flow through this resistor R1 is I1, and this is our resistor RF, and the current that will flow through this resistor RF, because the same current will flow through the resistor RF. So we can either call it I1, or let's say we define it as IF. Okay. So these two currents can be equated as I1 equals to IF, because one current is leaving the node and another is trying to enter the node. So let's see how feedback works here and what is the use of feedback. Okay, so let's say for some reason we have, so first we'll write these two expression. We know that the output divided by the gain is VID, okay, and VID is V2 over V2 minus V1. We can also write VID to be, but we then take the magnitude. We can also write V1 minus V2, okay? But then we have to take the magnitude of this to be sure to do the analysis. So let's say for some reason VI tries to increase. So when VI tries to increase, the V2 will increase. Okay, so because V2 will increase and V1 is equal to V2, so V1 will try to V1 will try to increase. Okay, or in a sense we can understand like this: when the Vi tries to increase, the difference voltage will try to increase. Why? Because the V2 is increasing. Okay, and the V2 increases, it means the VID goes up. And when your VID goes up, so obviously your output voltage is nothing but gate times VID. So VID goes up, V output voltage tries to goes up. This output goes up. So we are feeding back a fraction of this output at this node, that is V1. So V1 will go up. So if the V1 goes up right over here, so VID will try to come down. Okay, and it means V1 will increase because V2 has increased. So V1 will increase in the same proportion, and so that the aim would be VID goes to 0. VID becomes 0 right here. So this action is called as degenerative feedback. Degenerative or negative feedback, basically. So it's trying to force, this feedback is trying to force or keep the VID always to be 0. The difference between these two nodes is maintained at 0 voltage. Okay, so these two node voltages, operational amplifier, the feedback will try to make sure that the difference between these two nodes V1 and V2 is 0. Another case, if for some reason Vi goes down. So Vi goes down, it means V2 goes down. So if V2 goes down, we say that VID goes down. If VID goes down, so we know that VID goes down, output goes down. So output goes down, the node voltage at V1, the voltage at node V1 goes down. So it means first V2 went down, so Vi also went down. So it means in the same proportion, the V2 went down, V1 is also trying to go down. So VID will go down by the same amount as it went up. So final aim is that the feedback will try to push the VID, that is the difference voltage, to be 0. So again, this is called as degenerative or negative feedback. Okay, so that is the principle that we see here. So that's all for this explanation. So we continue with this operational amplifier and some more nice concepts in detail in a rigorous analysis that we'll perform right away.